Good afternoon, ladies and gentlemen. My name is Lilo van Lieshout from the International Life Science Institute Europe, and I would like to warmly welcome you to the webinar on relevance of microbial end product testing in food safety management that is organized by the International Life Science Institute ILSI Europe and by the International Association for Food Protection IAFP. We are happy to see that so many of you wanted to join us. I would first shortly like to introduce the organizing affiliations for those who do not know us. So ILSI Europe's vision is to build multi-stakeholder, science-based solutions for a sustainable and healthier world. ILSI Europe has a wide network with highly renowned voluntary scientists that discuss scientific issues of public interest. ILSI Europe is a non-profit organization with a tripartite nature, with very strict policy that we do not lobby and we do not discuss marketing and pricing. This again highlights the fact that we are a purely science-driven organization. More specifically, this webinar is organized by ILSI Europe's Microbiological Food Safety Task Force. Their main aim is to investigate microbial issues in foods that are related to public health risks. Current activities of the task force are related to antimicrobial resistance, industrial microbiological risk assessment, virus control options, and the use of meta-analysis in microbial risk assessment. ILSI Europe and IAFP already have a long-term collaboration in the organization of European Food Safety Conference every year. The IAFP has over 4,000 food safety professionals as members, and their main goal is to advance food safety worldwide. IAFP is particularly appreciated for their IAFP annual meeting in St. Louis, Missouri, in July until 3rd of August this year, and the IAFP European Symposium on Food Safety in Athens at the 11th to 13th of May. And we very much hope to see you there as well. Now I would like to give the word to Professor Zwietering to introduce the background of this webinar and to introduce the speakers.
Thank you, Lilo, for this introduction. And like Lilo mentioned, ILSI works on selected subjects in expert groups like the mentioned current subjects, antimicrobial resistance, risk assessments, viruses and meta-analysis. But before there has been an expert group working on history-based performance of the hazard control system to verify the effectiveness of food safety management from ILSI Europe. With as members myself, Lisbeth Jackson from Ghent University in Belgium, Jean-Marie Membré from INRA in France, Maarten Nota from the Danish Technical University, DTU, and Mats Peters from Nestlé Switzerland. And this work resulted in a publication in the journal Food Control, and at the same time in the USA, there was a question from the Office of Management and Budget, the OMB, that also resulted in a publication from Bob Buchanan and Don Schaffner in Food Protection Plans. And both these papers will be illustrated today. First, there will be a presentation by Mats Peters, then Jean-Marie Membré will continue, and then Don Schaffner. And after the presentations, there will be a question and answer session. We start this webinar with Mats Peters from Nestlé Research Switzerland, the chair of this ILSI expert group, about the role of validation, verification and microbial sampling in food safety management system. Please go ahead, Mats.
Thank you, Marcel. I'm working at the Nestlé Research Center in Switzerland, and I would like to say good morning or good afternoon to all of you. I will talk about the validation and verification of microbial sampling in food safety management systems. So, next slide. As an introduction, microorganisms can be heterogeneously distributed in a batch of food products, for example due to variability in raw materials, process conditions or way of contamination. Taking a sample is a stochastic process. The stochastic process is a sequence of random variables that change over time. And performing a sampling time is also a stochastic process. Testing methods are not perfect, for example, because of low sensitivity, and you can miss, for example, a pathogen in this case. And this raises the question, can end product testing control food safety? Due to the distribution of microorganisms in food, taking a sample for testing can be a lottery. And here is an example when you take 5 samples out of a batch of products. If taking a sample of 5 units from the upper right batch, all samples will come out negative, of course, and the batch will be accepted. But if you get such a result, you can hardly be sure that it's 100% right. Heterogeneous contamination can, for example, happen when the parts of raw materials are contaminated or when there is a failure in the process. If taking 5 samples from the lower batch, you may find a positive sample if you are lucky, but you may as well miss to sample from the part of the batch where there is a concentration of positive samples, and the batch will wrongly be accepted. In these 2 batches, where both has a homogeneous contamination, your testing may come out either as a positive or more probably a negative, as shown in this slide, even if there is a positive samples among in the batch. If 5 samples are taken, in one case we find 5 negatives, and in the next one we find 1 positive. Often we think that the first batch is free from contamination, and the next one is contaminated. But thinking about this with lottery, there is also a fair chance that both batches have an equal contamination rate. So in conclusion, positive means something, but negatives are no guarantee. And often we only take, for example, 30 samples of 10 grams, which is 300 grams, from a 30,000 kilogram sample. And then this is only 0.001% of the products. This graph shows the probability of accepting a lot under different conditions. The x-axis shows the proportion of defective products in the batch, and the y-axis probability to accept the batch depending on the number of samples taken. As you can see from the curves, the probability to accept batches increase with the number of samples taken. If, for example, the proportion of a batch of contamination level of a batch, I'm just looking for the pointer here, is 1%, which is down here somewhere. If you take 30 samples from a batch, the probability to accept the batch is 74%, which is somewhere here at this graph. And you can also say the probability of detecting contamination is only 26%. In conclusion, 1% of defectives in a batch, which is of course unacceptable when it's food products. This means that 1,000 products will reach the market and cause illness to the consumers. Due to the shortcomings of sampling, assurance of food safety are moving to activities that contribute more to controlling the safety than testing. This could, for example, be implementation of environmental cleaning programs and zoning to avoid recontamination of products or temperature controls to avoid growth in the production area. Therefore, it would also be beneficial if a history of compliance could merit a reduction of the required number of samples to test specifying legislations. Unfortunately, such criteria are rare, but there is one example where historical results of compliance can be applied to reduce end product testing in EU regulations. It says that salmonella in minced meat samples for microbiological analysis shall be taken at least once every week. But if all tests are negative for 30 consecutive weeks, the producer can reuse the sampling to every second week. The same is true if a national or regional salmonella control program can demonstrate that the prevalence is low. This means that testing can be reduced by 50%, which is very good from an economical point of view for the producer. So, just some quick definitions of validation, monitoring, and verification. Validation is the obtaining of evidence that a control measure, if properly implemented, is capable of controlling the hazard to a specified outcome. For example, to prove that 72 degrees C for 15 seconds gives a 6D reduction of listeria in milk. Monitoring is a planned sequence of observation of control parameters to assess whether a control measure is under control. And this could be a continuous verification in real time of the temperature, which should be 72 degrees at least, and the residence time in this particular case should be 15 seconds at least. Verification is the activity to make sure that procedures and other evaluations, in addition to monitoring, to determine whether a control measure is or has been operating as intended. And in this example, microbial testing to verify listeria absence in 5 times 25 milliliter of milk is a verification. These slides give a schematic overview of the relevant steps in the food safety control. One can have microorganisms in the raw materials, in the environment, and which can be present in the product if reduction or zoning is not working properly. If this happens, the microorganisms could come into the final product and grow there. Validation can provide evidence that the process will control initial levels of microorganisms in raw materials, the production environments, or transfer into the product. And by validation, a process is shown to be under control and be verified by epidemiological investigations on a governmental level and by end product testing by a manufacturer. However, neither absence of microbiological hazards in the finished product nor lack of evidence for an epidemiological link is a proof that the process is under control. But on the other hand, if finished products are not complying or there is a strong epidemiological link, this can be an indication that a process is not under control. And in this case, the verification activity in terms of sampling, that is useful. This flowchart shows the general process that should be under control for safe food production. It's very simplified, of course. The flowchart shows that the inactivation eliminates microorganisms and recontamination is prevented and production is under control. And if microorganisms are still present in low numbers, prevention of growth, for example by short shelf life and chill temperature, will keep the level low until the consumer consume the product. This can also be expressed mathematically. If reduction is high and recontamination is low and growth is low or zero, the process is well under control and the concentration in the finished product will be low. If a process that should ensure inactivation and prevention of recontamination and growth are effectively controlled and show excellent historical records, it can be questioned whether testing is a useful tool and don't provide much to control food safety. Some examples of information sources for validation. This is scientific literature, databases, baseline studies, predictive microbiology, risk assessment, specific experience, for example, challenge tests. And for verification, microbial testing that the producer do themselves, consumer complaints and authority testing, and reports on outbreaks, zoonosis, and recalls. Management of food safety should ensure that hazards are under control, and the implemented control measures provide a final level of the hazard that is not causing harm to the consumer. As mentioned, food safety is built on a number of different blocks that are put together into a pyramid, like ERPs, HACCP, validated control measures, and monitoring. If validation and monitoring shows that the process is under control, this can be verified by finished product testing. However, if one or several blocks in the food safety pyramid breaks down, the whole foundation of the food safety system will fall apart like a house of cards, and end product testing will then on its own not guarantee that food is safe. So to the conclusions, all samples negative is no guarantee of safety. And a positive sample is indicating unsafety. Sampling is useful for verification. And control of safety is only very limited extent supported by end product testing. And with this, I give the floor to the next speaker, or give the line maybe, with some case studies on canned foods and cooked sliced ham. Thank you.
Okay, thank you very much, Mats. So the next speaker is Jean-Marie Membré from INRA in France, who will illustrate the concepts that have just been explained with the examples canned foods and cooked ham. So I give now the floor to Jean-Marie.
Okay, Marcel, thank you. And good morning to everyone. Good morning or good afternoon, actually, to everyone. So, yeah, I'm going to go through two examples. And so just quickly to introduce and just to say again that these two examples were actually analyzed in the work that we did at ILSI. So first, the example of canned foods. So if I start with raw materials, so you've got the preparation of raw materials, filling, seaming, and seaming is very important because at that stage you get really hermetically sealed can. And after the seaming you get the check of the weight and then the sterilization. And the sterilization is very high as well for Clostridium botulinum, currently for non-acidic and ambient stable products. The heat treatment is as high as 3 minutes at 121 degrees. And actually in practice is very often higher than that because you get as well the spoiling spores. So because of that it's even higher than that. So considering that this heat treatment is very high, it is there is a very, very low probability of surviving spores after the sterilization, spores of Clostridium botulinum, of course. And the same, the recontamination, let's say that we can say that it's prevented. So if I summarize that, the same diagram, but with only the 4 key steps. Introductions of Clostridium botulinum at the raw material preparation step, it's possible. But the sterilization by heat treatment is very effective. And the recontamination after the treatment doesn't make really sense in this case. So because of that, considering any growth at storage is also irrelevant. So if I put everything together, that means that the percentage of contaminated end product is going to be very, very low. And when I say very, very low, that's definitively less than 1 in 10,000 per product. But I need a figure to illustrate a little bit more. So let's considering that this figure is 1 in 10,000. And how can I verify this statement? I can use actually external sources of information, and particularly in this case, if we check what we got in the WASP portal, so the European Rapid Alert System for Food and Feed, in 16 years there were 3 notifications of Clostridium botulinum in canned products. And from the EFSA reports, we got a little bit more. We got about 10 outbreaks per year. Could seem relatively high, but first, keep in mind that the outbreaks don't come systematically from industrially canned products, actually very often from homemade products. And also, just put this figure in perspective of the annual European domestic market of canned products. It's 8 billion kilo of canned products. So the ratio, so the rate is still very, very small. So move on now to the sampling plan, and is it relevant to do any sample with canned products? So with the same plot as previously shown by Matt Spitter, you see that 1 per, let me try to show that here, yeah, 1 per 10,000 is really on the corner on the left of the plot. So if I try to calculate how many samples I need to get an effective sampling plan, so by an effective sampling plan, I say a sampling plan who can detect with 95% chance that the batch is contaminated. I need to sample a lot. Actually, what I need here, and yes, it's to sample, 1 per 10,000. I need to sample to a level very close to 30,000. So that is huge, and to be honest, completely unrealistic. So, in that case, and after I will move to the other example, but for this example, I can conclude that with a so small expected rate of defective end products, sampling is ineffective. Move to the second example, sliced cooked ham. Okay, so we start with receiving the raw materials, cutting and deboning, brining, tumbling, forming, so a lot of preparations, but after cooking. And we can still consider that the cooking is very effective. But now we are not talking about Clostridium botulinum anymore. We are talking about Listeria monocytogenes. So 70 degrees for 40 minutes is effective to inactivate all the bacteria which could be in the raw material or which could be brought by all the handling that are done before the cooking. So then, we've got the cooking, which is nice, cooling, and unfortunately, after the cooling, we've got the slicing. And of course, at that stage, we have to handle the product again. And that will enable to have recontamination by Listeria monocytogenes. And as you know, Listeria monocytogenes is able to grow under chilled conditions. So even if we store all the cooked ham in chilled cabinets at retail and at consumer place, there are still a chance to get bacteria growing. So let's summarize that with the 4 key steps as I did before. At the raw material stage, yes, it's possible to have an introduction of Listeria monocytogenes. The cooking is still very effective to remove them, but and that is the difference with the other case. But now the recontamination is possible, particularly due to the slicer. And then, as you got some bacteria, And as the storage is at low temperature and Listeria is able to grow at low temperature, you get you have a lot of chance to get growth. So overall, that means that the percentage of contaminated end products might be non-negligible this time. So how can I verify this statement again? Again, by using external sources. And here I'm going to illustrate with the WASP portal, the EFSA reports, but also with literature studies. Start with WASP portal. There were 19 notifications in 60 years, 8 from companies' own tests and 11 from official tests of products on the market. So that is still relatively low, but that happened. But more importantly, the EFSA reports. They said that, in average, 5.1 of samples from pig meat cooked ready-to-eat products, so not specifically ham, but really close to ham, collected at retails were Listeria monocytogenes positive. So please pay attention. That are Listeria monocytogenes positive. That doesn't mean outbreaks. Actually, there are no outbreaks with these products. But this number, 5.1%, is quite high. And if I check the literature, and we did that as well, from with survey done at retail for different countries, and overall you can see that the prevalence varied between 0.9 to 6.9, which is not at all negligible, and the average is 3.2%. So, building on literature and epidemiological data, we can say that the prevalence is relatively high, and that, sort of verification of what we saw when we analyzed the process diagram. So, let's keep going now with the curve here. Here that the 3.2% corresponds to 1 per 31. So 1 per 31 is still very small. So if you have only a sampling plan with 1 sample, 2, or even 30, you still have a lot of chance, that is not really a chance, it's more budget, to accept the batch. So what do we need? Actually, we need to sample more. And in that case, we need to sample to the level of 92 samples. And again, to get 95% chance to pick that the batch is contaminated. Just a simple rule of thumb, because if you are not too familiar of statistics and these calculations, there is a curve which is, of course, used in first approximation, but very, very nice. You get here the defective rate. When I say here, it's here. Yeah. Defective rate expressed as 1 in X, so let's say 1 in 31. And here you just multiply this X by 3, and you get the number of samples to be sure that you detect with 95% chance. So when you get 30, which is around here, you get 100 roughly. And in the other example that I showed, with the canned product, it was 1 in 10,000, so that corresponds roughly to this point, 30,000. Okay, keep going with that. Important to keep in mind that sampling 92, so having a 92 sample, is still very high because the European Commission recommended a sampling of plan of 5 units. So 5 units correspond to the blue line, which is pointed here. And just if I zoom on it, a plan with 9 samples has still 85% chance to accept the batch if the defective rate is 1 per 31, so it's not yet really effective. So, what is effective actually? What is effective in terms of food safety management is to have control measure and to prevent recontamination by Listeria monocytogenes at the slicing steps. So we need really to have best practices on cleaning and operations of the factory environment around the slicer and packaging equipment. And in practice, what does it mean? It means that we need to have a sampling plan, yes, but at the environment and the equipment around the slicer. So, you know, all of the equipment in contact with the product, the floor, etc., and not at the end of the end product. And here we've got an example which was actually prepared by the Food Safety Authority of Australia, and it's on cooked ham. And they really explain, and the document is fully available, so it's quite good to have a look to this document. But what they say, for cooked ham, they say that business operators have to sample 5 environmental sites for Listeria monthly. And what they advise is actually, they say that in case of positive samples, immediate investigation has to be carried out, of course, but also after that, you try to address, you know, the problem, and after, instead of sampling monthly, you start to sampling weekly, up to the level where you get 3 consecutive negative sample results. Okay, so I think I have more or less finished now, and I will move to the conclusions. I hope that I have illustrated with my 2 examples that assurance of food safety cannot be based on end product testing. An efficient food safety management system must be implemented. And it has to be based on HACCP principle and with proper prerequisite programs. What is important is to identify what the crucial steps in the process are, and then to monitor results at CCPs. That is really, really critical, very, very important. You know, that will enable to pick if there is any variability or any problem. So if I illustrate that with my 2 examples, the canned products, definitively the thermal process is a crucial step. So relevant records could be temperature and holding time at the sterilization. Cooked ham, the slicing step is a crucial step. So in that case, cleaning procedure in the environment and the slicing machine and so on is crucial. Just to finish, and to be a little bit positive considering end product testing, I would say that end product testing is used for verification of the implemented food safety management, and that it can really be used in that case.
Jean-Marie, are you still there? Jean-Marie, are you still there?
This is Don. Can I suggest that I just continue since Jean-Marie was wrapping up?
Yes, please do, Don.
Thank you. So what I want to talk about, so first of all, thanks to both to Matt and Jean-Marie for providing those 2 previous talks. Matt started from sort of a high-level perspective. Jean-Marie took us down into the details. I'm going to pop us back up to a little bit higher-level overview, and I want to specifically talk about testing as a tool for verifying preventive controls. And as a way of a background, I want to let you know that for those of you who are not familiar with the preventive controls rule, which just recently came out as a final rule here in the United States, This rule was sent by FDA through the rulemaking process, and it actually stayed for 1 year in our Office of Management and Budget. And during that time, OMB struck out a number of provisions that FDA had put in the rule regarding product testing. Now, myself and Bob Buchanan were approached by the Pew Charitable Trust in 2013 to basically, not necessarily to address that issue, but to talk about, from a scientific perspective, what the role of microbiological testing in the context of the FSMA preventive controls would be. And the idea was that we would write this report for the Pew Trust, and then they would use that report in turn to inform their comments on the proposed rule. Now, of course, now we have a proposed rule. We do see that there are some testing provisions back in the rule. I'm not really going to talk too much about the rule, but I do want to talk about testing in the context of food safety and the rule. I also want to mention that if anybody is interested in my comments in more detail, we had an article published in Food Protection Trends earlier in this year, and certainly anybody who's interested can read that article. Okay, so let's dig into the details. First of all, I do want to clarify a couple of definitions, and again, you may have heard the previous speakers talk about these, so I'm not going to spend too much time. I do want to distinguish between monitoring and verification and validation. Monitoring is real-time measurements and observations that are taken. These, for those of you who are familiar with HACCP, these are the typical measurements that one would make while implementing a HACCP program. These monitoring measures are designed to ensure proper functioning of the food safety system. That's in contrast to verification and validation. Verification and validation deal with the questions of, is the system continuing to function as intended? And I want to spend just a little bit of time and talk about verification and validation, and I know Matt touched on this earlier, but I just want to come back and revisit it here briefly. So, for example, if your HACCP plan says you're going to cook your food to 160 degrees Fahrenheit, 71.1 degrees C, and in fact you cook the product to a higher temperature, then you have verified that you are following your HACCP plan. If your plan says, again, the same thing, cook to 160, but you do not cook to that temperature, then your HACCP plan is not verified. Now, that is different than validation, okay? And people often, in my experience teaching this, validation is confused with verification. If your plan says, and validation really deals with scientific accuracy, if your plan says you're going to refrigerate to 45 degrees Fahrenheit to control salmonella, that's actually a scientifically valid statement. However, if you say you're going to refrigerate to 45 degrees Fahrenheit with the expectation of controlling listeria, that is in fact an invalid statement. That is a scientifically invalid statement, and you cannot control listeria by refrigerating to 45 because in fact the organism will grow at that temperature. So with that as a prelude, let's move into a few more definitions before we get to the meat of what I want to talk about. We know today that we want science-based regulations. What does that mean? Well, what science-based regulations are, these are regulations that use the best available scientific information within a regulatory framework. So, for example, using temperature limits to control the growth of salmonella versus Listeria monocytogenes. Another example is if you can use indicators as a way of monitoring whether you are controlling pathogens, but only if you know definitively that the presence of those indicators correlates with the presence of pathogens. Now, another issue that we want our regulations to be, or another feature that we want our regulations to have, is we want them to be risk-based. And I want to briefly talk about what it means to be risk-based. According to Codex Alimentarius, risk is a function of the probability of an adverse health effect and the severity of that effect consequential to hazards in food. That's a bit of a mouthful, but basically what that means is that a risk-based system considers probabilities. And so you might have a hazard in one food and the same hazard in another food, but because the probability of the occurrence of that hazard is different, or the consequences of that hazard appearing in the food are different, then you are going to manage those risks, you are going to manage those hazards differently because the risks are different. Okay, let's bring it back to microbiological testing. There are basically three types of testing that one might have in a food system. Traditional lot testing, and that's what many of us think of when we think of testing. Environmental testing, which I'm not really going to talk about today, but which does certainly play a very important role in FSMA and indeed in food safety around the world. What I mean by environmental testing is testing the environment for the presence of either pathogens or indicators, and then using that to control the safety of your food product. And then finally, the last kind of testing, and this is what I want to spend most of my time talking about, is process control verification testing. This is not the same as traditional lot testing, and I want to illustrate for you what process control verification testing is and why it might be useful for you. So, traditional lot testing, the classic example here is a lot of product that you have no information about. Let's say it's coming into the country, it arrives at a port of entry, and you need to make a decision about whether to let that food into the country. If the shipper of that food is following HACCP, then traditional lot testing should not be needed. But where it does come into use in today's food system is if you are following a test and hold or a hold and release program. And in that case, that testing is serving as a preventive control, and it's not a verification tool. And again, we heard excellent presentations just earlier in this webinar on the fact that effectiveness of testing decreases substantially when that defect rate is low. And you saw some amazing numbers from Jean-Marie's presentation, which showed that basically the number of samples you would need to test to ensure that a batch of product was meeting a very, very low defect rate, it becomes cost prohibitive or becomes ludicrous fairly quickly. Also, another problem with traditional lot testing is if you are testing that food product and you are not releasing it, you are not shipping it until you get the results of that testing back, and if you have a food product with a very short shelf life, it is going to be very, very difficult to actually get that product on the market with any kind of shelf life left because you're waiting for the test results to come back. So there are definitely some limitations with traditional lot testing. Okay, as I said before, environmental testing is testing of non-food contact surfaces and food contact surfaces. It is a verification activity. It may also be a sanitation control point, and what I mean by sanitation control point, I'm sure many folks that work for food companies who are on the call today may have an ATP testing program using some bioluminescence monitors, not necessarily for the presence of bacteria, but it might indicate bacteria, it might indicate food debris, and you can do that as a sanitation monitoring activity. And again, I could go on and give an entire lecture on environmental testing, but that's not the purpose of my talk today, so I'm not going to do that. What I want to do now, in the time that I have remaining, is I want to talk about process control verification testing. Now, process control verification testing is something that may be a new concept to many of you on the call, and so that's why I want to focus on it. Let's consider, for example, that you are producing a food where you have a 5-log thermal inactivation of salmonella. And you have prior surveys that indicate that the level of salmonella in your raw material is less than 1 colony-forming unit per 100 grams of product. How do you ensure that 5-log reduction? Well, you have monitoring. You monitor time and temperature during the thermal process. The verification comes in when you periodically examine that finished product or indicator organisms or for salmonella. That is an example of process control verification testing. Now, let's look at what happens when you have an issue with that. For example, if you are your critical control point monitoring indicates that everything is fine, that you are apparently delivering your 5-log reduction, but you have a test result that either shows the presence of salmonella, which should not survive that 5-log reduction, or some other indicator organism, generic E. coli, for example, which also should not survive that 5-log reduction. There are at least 3 possible explanations for that. First of all, could be that your raw material had a very, very high level of salmonella. There was some incident in the field or in raw material handling that significantly increased that level of contamination. It could be that you had cross-contamination or you had post-process recontamination. Okay. A third possibility would be that even though your monitoring indicated that your thermal process was acceptable, it could be that in fact you had a defective thermocouple or you had a miscalibrated thermometer, that something in that thermal process that you believe was in fact correct was in fact not correct. Okay, and this is an example of what I mean by process control verification testing. The way that this works is you can conduct a limited number of tests across lots of product over time. This is in contrast to the first type of testing that I talked about, right? The batch testing, where you are testing many, many samples of the same lot, okay? And with process control testing for verification, you can use something called statistical process control. And we have some examples of this in U.S. regulations. For example, a lack of generic E. coli in 2 10-ml samples per 1,000 gallons of juice, 2 positive assays in a moving window of 7 consecutive samples. Or another example would be testing for salmonella once a day using a presence-absence test, and then again having more than 1 positive sample in a 7-day period, indicating loss of control. We have something not quite that, but something analogous to that in our meat and poultry regulations for raw meat as an indication of process control. Okay, so getting close to the end here, and I'm almost out of time. This concept that I'm going to share with you on this slide here, slide number 51, is expanded in more detail in my article with Bob Buchanan, and so if you have more questions, I encourage you to take a look at it. There are certain circumstances where process control verification testing should be used. And basically, you need to go through the checklist that's provided on this slide. If you can answer yes to all of the 5 questions on this checklist, then it is okay to proceed with using process verification testing. Okay? So, first of all, are you currently doing test and hold or hold and release? If you are, you cannot do process verification testing. Those are incompatible. Are the practices that lead to an increased pathogen risk known? If they are known, then you can use process verification testing. If you don't know what causes the pathogen level to go up, you cannot use this because you wouldn't know what to do if you found a pathogen. Third question. Is testing, in fact, feasible? Is there a commonly available test for the organism of choice or appropriate indicator? Is it affordable, et cetera, et cetera? For example, if you want to have a test for norovirus, well, guess what? There's no way to culture norovirus, so you're going to have a hard time perhaps finding a test, or maybe a test for a parasite. Again, not going to be commonly available, not going to be affordable, so probably not appropriate. Fourth point. Are there indicators or pathogens themselves that can be used to check for loss of control? Because remember, with process verification testing, it's all about determining whether your process is in control or not. If there are no indicators or pathogens that are an indication of loss of control, you cannot do process verification testing. And then finally, and this last one is kind of the most interesting one, is there regulatory or industry guidance on appropriate levels of the indicator organisms or of the pathogens or of the frequency of pathogen contamination? Now, if the answer is no, then you can still do process verification testing, but you're going to need to go out and collect additional data to find out what those appropriate levels would be. And of course, if you already have regulatory or industry guidance on appropriate levels, then, and the answers to all the other questions are yes, then you can use process verification testing. So, in summary, not all microbial testing is the same. Traditional lot testing is what most of us think of, but it's only one small part of testing. Environmental testing is going to be very, very important, I think, in the years to come. It was not a focus of my talk, but it is a type of testing that's important. And then finally, my main point was to make you aware of this concept called process control verification testing. I think definitively testing does have a role to play in assuring food safety. And if you want more information, please do consult our article that was published in Food Protection Trends earlier in this year. Again, if you'd like, I'm sure Bob and I would be happy to provide you with a copy, but you can also get a copy on the IAFP website. With that includes my remarks, and I want to turn it over to Marcel to manage questions. Marcel.
Okay, thank you very much, Don. I hope people can hear me. I was disconnected for a while, but fortunately I came back. So I would like to thank all the three speakers, and especially for being very accurate in their timekeeping. They were all three excellent, I think, in keeping to their time. So there is now 10 minutes for answering questions, and several questions came in, and they will now be presented on the screen. And I hope that everyone can see these. Let's start with the first question. That is one of the points that is made, and that was a question that came in already by email. Viruses and emerging microbial pathogen challenges this concept. They may not react as expected from the taxonomical classification. And your opinion, what would be the best approach to address these issues? So the testing of viruses and emerging microbial pathogens. And I would maybe ask Don to respond to this question. Is that possible, Don?
Sure, absolutely. So again, as I said, it would be possible to do process control verification testing with these organisms, but as I indicated, you really need to have a readily available test. I think in many cases, the good news is that viruses or parasites will often be associated with indicator organisms. And so if I was faced with a challenge of managing this issue, the first thing I would do is I would look to see whether there was correlations with indicator organisms. If they're not, the good news is that we are continuing to see advances in molecular methods for testing for these organisms, and certainly those methods can be used. With those methods, you have to be a little bit careful because they can detect live as well as dead organisms. But I think, it certainly is an issue right now, but the good news is there are a lot of smart people working on better methods and, being able to culture norovirus hopefully soon and those sorts of things. So, but there are still some real challenges today that we don't have the tools to deal with yet.
So the next question is, the presentations explained how to decide whether and if useful of validation and verification of production process. What can be said about monitoring and retail of such products in terms of numbers of samples? And later on, the person that asked this question also added to this, at the low defect rate, how useful is this market sampling for monitoring purposes? I don't know if Jean-Marie is again connected. Are you online, Jean-Marie, or are you still disconnected? I don't hear anything much. Will you be able to answer this question?
Yes, I am connected, and yes, I could at least partially to answer this question. If I take back, the example of cooked ham, as Matt said, by in terms of validation, we can use predictive models and risk assessment. And in the case of Listeria monocytogenes, from the level expected at the manufacturer release, after it's possible to, using WRF models particularly, to estimate more or less accurately, but in the case of Listeria, it could be very accurate, the level that you have in retail at different times. So because of that, maybe you can really have a specific sampling plan to verify the level that you expect to have in your product. But again, that would be for verification more than really to control the supply chain.
Okay, the next question is how to deal with strain variability with regards to validation. So that's more not towards the end product testing, but towards the validation and the impact of strain variability. Maybe that could also be answered by you, Jean-Marie?
Yeah, my first thought about that, is by risk assessment and taking, the variability in a probabilistic model. But that means that we need to have a lot of data on that to get something relevant. Yes, my first thought is going to using risk assessment. So analyzing the process steps as we did schematically here, but with probabilistic models to include the variability and the strain variability.
Okay, and the next question is the next question was related to the last presentation. So how can you reliably detect such low levels of salmonella? Don, could you answer this question?
Well, the issue is, remember, with process control verification testing, the issue is not detecting low levels of salmonella. It's determining whether your process is in control. If you do have very, very low levels of salmonella and you know there is a reliable indicator, Enterobacteriaceae or generic E. coli, that works as an indicator, then that can help with that issue. But there's no way around the fact that if you have low levels of salmonella, they're going to be difficult to detect.
And also to the last presenter, so how likely is it to find unknown errors? That's if it's unknown, so that is rather difficult, Don, but still a question for you. So high level in raw materials, new ways of recontamination and process control verification testing. In other words, how effective is process control verification testing knowing that defect rate will be very low?
Well, I guess what I would say is, being a guy who does modeling and risk assessment, and I would be curious on your thoughts on this, Marcel, as well. If you could simulate some of that and figure out, what the possibility would be if you had high levels in the raw material, how high would they have to be? What would be the probability that you would detect that? If you could make estimations about recontamination rates, etc. So I would take a numerical simulation-based approach to figuring out how effective it would be given certain changes.
Okay, then I would like to go to the last question. If the whole chain is managed through HACCP, then it would be possible to guarantee safety as opposed to end product testing. This calls for all chain actors to be meticulous in their role. Simply put there as needed. So the question, one way or another, is this calls for chain actors. I'm sorry, it's working on its own. But this calls for chain actors to be meticulous in their role. Simply put, there is a need to create awareness, re-energizing, and cooperate along the chain. Mats, could you give some thoughts on this remark?
Yeah, this is hypothetically that everything is controlled by HACCP. And we know also that not all producers have a HACCP plan even in many countries. So this is not possible, in fact. Of course, people need to be aware about food safety, but there are always people around which don't care about it, or they don't know. In many countries, there is the level of education and so on is not sufficient to take to do a HACCP plan, in fact.
Okay, I would now like to hand over to Lilou for the closure of this session. Lilou?
Yes, thank you very much, Marcel. Yes, this is already the end of the webinar, and therefore I would like to very much thank Dr. Mats Peters, Dr. Jean-Marie Mambré, and Professor Donald Schaffner for their invaluable contribution to the presentation today. And thank you very much, Professor Marcel Zwietering, of course, for the moderation during this webinar, and Dr. Liesbeth Jackson and Professor Robert Buchanan for being available to answer questions and to help developing the slides and the webinar structure. And also many thanks to the IAFP staff, of course, mainly Dina Siedenberg, that facilitated all the technical details for this webinar, and IAFP for co-organizing this. And of course, thanks to all my colleagues at ILSI Europe, the Microbiological Food Safety Task Force, and for all the participants that joined us today. I wish you all a very happy evening and a happy Thanksgiving Day for those of you who will celebrate it tonight. And that depends, of course, from where you are. And we are looking very much forward to having you again in our next webinar or our next activities. Thank you very much.